Hi everyone. So last lecture we talked about concrete formwork, setting up the form boards and getting ready to pour. This is going to be kind of a companion lecture to that. We touched on a lot of the components in that last lecture, rebar briefly, talked about anchor bolts briefly, but here I want to go a little more in depth, get a little deeper into some of these things that need to go into the formwork before we pour concrete. So let's start with rebar. And remember, I talked about how concrete has really high compressive strength. If we're trying to crush concrete, we're going to have a really hard time. If, however, we try and pull concrete apart, okay, and more specifically, we're talking about like if the concrete isn't supported well underneath, it'll want to break, okay, that's tensile strength. And so when we add steel, and most of the time that's going to be in the form of rebar, we can add tensile strength. Remember, some people use welded wire mesh, and again, that's that 1/4-inch rod that's welded into a big sheet, and you place that in the concrete and you make sure to kind of pick it up as you're pouring so the concrete gets all around it. When people are making concrete countertops, they will add, you can get a bag of like fiberglass chips and cast that into the concrete and mix that into the concrete, and that can add tensile strength to the concrete as well. I've heard a couple stories of people trying to do actual slabs with those fiberglass chips and leaving out the rebar, and apparently it didn't go very well. I might look into that a little bit more because I remember it was something I was hearing about, like, oh, we're never going to use rebar again. We're going to use this fiberglass now, and then I never heard about it again. So I don't think it really worked out. So for now, rebar is kind of the go-to method for adding tensile strength to concrete. Again, something I want to reiterate, try and resist this idea, and everybody has this idea that you put rebar in the concrete and then it won't crack, okay? The concrete's going to crack. I guarantee it. The concrete will crack. What the rebar does is it prevents that concrete from separating when it cracks, okay? I would I would go out on a limb and say by adding steel, you will get fewer cracks than concrete that doesn't have any steel added. But just try and understand how this is working, okay? It's not this magic thing that stops the concrete from cracking. It keeps the concrete together when it cracks, okay? So, ordering rebar, describing rebar to people, the way we typically do that is saying, like associating a single number with it, okay? And that number is relative to the diameter of the rebar, okay? So if I say number 4 bar, I need a bunch of number 4 bar. That is the number of eighths diameter of the bar. So number 4 bar is 4/8 of an inch thick, okay? If I say I want number 5 bar, it's 5/8 of an inch thick, okay? It is perfectly acceptable to say 1/2 inch bar, 5/8 bar, 3/8 bar, okay? Some people, there are certain lumber yards around town too that I'll go and say, oh, I need some number 4 bar, and they don't know what I'm talking about. And then you say, okay, I need a 1/2 inch bar. But the industry standard is to refer to it as number 4 bar, number 5 bar, okay? And again, that's referring to the number of eighths in the bar. Okay? It can be kind of confusing, but get into the habit of referring to rebar in that way, okay? Most of the rebar that we use in residential construction is going to be number 4 bar. Okay? We'll talk a little bit more about this. There's one other delineation that needs to be made with rebar, and there's 2 different grades of rebar commonly available. Grade 40 or grade 60. Grade 40 is definitely the standard, most readily available grade of rebar. And what that means is that it can withstand 40,000 psi before it breaks. Okay? Grade 40 can withstand 40,000 pounds per square inch. Grade 60 can withstand 60,000 pounds per square inch. Okay, so why does this matter? Normally, it doesn't really matter. Normally, we're just using grade 40 rebar and putting that in our foundations, and it doesn't really matter. Every now and then, the engineer will determine that we need grade 60 rebar. And that's something that you need to be checking the plans and seeing that it says, okay, grade 40 rebar, this is what we're using. If it calls for grade 60 bar, you need to obviously buy grade 60 bar and put that in your foundation and save the slip that says I put grade 60 rebar or I bought grade 60 rebar, because it's likely that when the inspector's looking at the plans during one of the inspections, they're going to see that grade 60 rebar is called out, and you want to be able to verify, like, oh yeah, well, we used the grade 60 rebar. Otherwise, there's a chance that you're going to be tearing that rebar out and replacing it, because this structure has been designed to withstand the loads that are going to be placed on it with grade 60 rebar. So you need to make sure that you're using the rebar that's been called out. Okay. This is a nice section cutaway view of our foundation plan here, and I want to talk about this a little bit. So we are looking at our stem wall right here. Okay, this is like the end view of the foundation. This part is the footing. Okay, it's wider than the stem wall. Generally, it's 12 inches wide. Depending on what kind of soil we have, maybe that footing is going to be wider. Okay, but 12 inches, a one-story building, that's the most common. Okay, this taller rectangular part, that is the stem wall. That's the part that we're going to attach form boards, stake form boards up, pour concrete in there, strip the form boards off. A lot of this is going to be visible. We're going to backfill against part of that stem wall and cover up all the footings in part of the stem wall. Okay, whoops. We want to look at the plans, and here it is right here. It says number 4 rebar, T and B, that stands for top and bottom. And that is the most basic rebar formula for a stem wall. Okay, we're going to have one stick of number 4 bar running the length of the foundation at the top, 3 inches down from the top, 2 to 3 inches from the top. We're going to have one stick of rebar running continuously along the bottom on the footing, 3 inches up from the bottom. Okay. Number 4 bar, again, that's half-inch rebar, is the most common. When this would change is when we have a really tall stem wall. And I talked about that in the last lecture. If we have a stem wall that is 4 feet from the bottom of the footing to the top of the stem wall, if it's more than 4 feet, we need to get an engineer involved to design a stem wall that's not going to topple over. Okay? It starts getting too tall, it starts getting top heavy, and then the concern is, oh, we've got this really tall foundation wall here. Somebody's going to come along and backfill a bunch of dirt against it or crash into it with a tractor or something like that, okay? If this was backfilled on equal sides, it wouldn't be a big deal. There would be equal loads applied against it and it wouldn't have anywhere to go, okay? But when you just backfill one side of a really tall wall, it puts a lot of weight against this wall and you could have failure, okay? So, getting a little into the woods here, let me back up a little bit. What typically happens, let's say our stem wall is going to be taller than 4 feet. I'll go back to the engineer and say, oh, we got this stem wall that's 5 feet tall, okay? And the engineer will ask me some questions like, oh, well, you know, how much are you going to backfill on this side? And I'll give them a number. And then usually they kick a design back pretty quickly. They have a pretty generic design. And usually what it is, okay, you were going to use number 4 rebar, top and bottom, and in the middle. Bump that up to number 5 rebar. And then now you're going to have vertical rebar as well as the horizontal rebar, okay? And the spacing varies, but typically it's 12 or 16 inches on center for those vertical bars. And what they're going to do is we're going to tie into this top bar, tie into that top horizontal bar. It's going to come down and it's going to have a little hook that toes into the footing. And every other bar is going to alternate the direction of that hook. Okay? And that's your pretty typical engineered stem wall design. Number 5 horizontal bar, number 5 vertical bar with little hooks on it, alternating direction. Okay? Hopefully that makes sense. And we've done this in the past. We've had some really tall stem walls before where we've had to do this engineered wall. So, but anyway, let's move on a little bit here. This picture is a concrete block called adobe. Okay, D-O-B-I-E, Dobies. They come in bricks, I forget how many, 25 per, and you break them up with your hammer, and they've got a little piece of tie wire embedded in them, and you can wrap the tie wire around the rebar along the footing for that footing bar. Okay, we don't want the rebar to come in contact with the dirt. It can't be sitting on the dirt. There's 2 reasons for that. The first reason is if the rebar is sitting on the dirt, it's not encased in the concrete. It's not adding any sort of tensile strength at all to the concrete if it's all the way at the bottom. If it has a ½ inch of concrete covering it, it's not doing any good. We want concrete to fully encase that rebar, okay? The other reason is we don't want it touching the dirt because the dirt is going to be wet at certain periods throughout the year. When the dirt's wet, the rebar is going to get wet. When the rebar gets wet, the rebar is going to rust. And when rebar rusts, it expands and it pops the concrete. It'll break the concrete. And that phenomenon is called spalling. Okay? Spalling is kind of like late stage concrete failure. Okay, and this happens. You'll see this around. There's some examples like the old Daly building downtown, which is now the Arkley Center for Performing Arts. This is kind of a minor example, but there were all these plaster reliefs on the outside of the building, and they had wire mesh embedded in them to give them some tensile strength, which was a great idea. But then 60 years later, everything had gotten wet, it expanded, and they were just popping right off the building, okay, falling on people's heads and stuff. So they had to kind of redo that. I saw when I was in Santa Cruz, I have a friend that works at one of the labs, one of the oceanic labs, and there were some concrete pillars that were constantly getting washed by the ocean, and they were spalling like crazy, blown in half. You could see the rebar. It was a complete failure. Okay, so can't be in contact with the outside air, can't be in contact with the dirt. Okay, there is fiberglass coated rebar for circumstances where you're going to be pouring concrete in salt water, something like that. Okay, but for the most part, we'll be fine for a while. But eventually, rebar is going to be the doom of all concrete structures. Okay, unfortunately, that's just the case. Rebar is going to be the doom of all concrete structures. It adds an incredible amount of tensile strength, but concrete is not completely impermeable. Water will seep in there. Water will rust that rebar eventually, and that rebar will spall the concrete eventually. Okay? So, I think that, well, one more thing. I want to talk about this top bar. This top bar is going to be suspended from the top with some tie wire. And as we're pouring, it's somebody's job to make sure that that top piece of rebar and these intermediate pieces of rebar stay in place during the pour. The concrete has a tendency to, as it's getting pumped, push that rebar over to the side. And sometimes we need to kind of yank that back into the center of the formwork. Because if it gets pushed all the way to the side, first problem is we don't have concrete all the way around that rebar fully encasing it. And then the other problem is we strip the forms off the next day and uh-oh, we're seeing rebar in the concrete. That's really, really bad. That's really, really bad. Okay. And then one more thing about this detail that I missed here. We're going to have a piece of rebar at the top. We're going to have a piece of rebar at the bottom. And then we can't have any more than 18 inches between those two sticks of rebar. Okay. So if our stem wall is relatively short and we put in a piece of bar at the top and a piece of bar at the bottom, and we have 17 inches from that bar to that bar, we're done. We don't have to add any more rebar. Okay. That's the code minimum. Maybe we want to add another stick of rebar, but as soon as we exceed 18 inches between the footing bar and the top bar, we're adding an intermediate bar. Okay, another one that's going to run horizontal throughout that formwork.